Alright, if we're asked if these two functions, f and g, that are presented as lists of points here, if we're asked if they're inverses, there's a short way to do this and there's a long way to do this. Now, we've already been asked to find all of this stuff, but suppose we weren't asked to find that. And we were just asked, are f and g inverses? Well, let's look at f first. It is a function because none of the x coordinates or the first entries are repeated, and it's one-to-one because none of the second entries are repeated. So f is a one-to-one function, and if you have a one-to-one function and you have a finite list of these pairings, then the way to get the inverse is just to swap the x and y coordinates. So that's f inverse, and sure enough, f inverse and g are exactly the same thing. So the short answer to that one is yes. Now, suppose you've already been asked to find all of these. Okay, so let's just do them, and that's going to be f evaluated at g of 11, and you can see that g maps 11 into 0. So that's going to be f of 0, so g of 11 is equal to 0, and f maps 0 into 11. So we have that. Now that in itself is not proof. You have to do it for everything that's in the domain of this. But these are small enough to where we can check everything. So that's going to be f evaluated at g of 5, and if I go into g, where does it take 5? It takes it into 8, so g evaluated at 5 is 8. And now what's f evaluated at 8? F evaluated at 8 is 5. And once again we have this. So again, it's not proof that they're inverses, but if just one of these doesn't work to where you get the same thing, then they're not inverses. But to prove that they are, you have to go through every single possibility. So the last thing in the domain here for f composed with g is 7. And what is g evaluated at 7? It's -3. And so what's f evaluated at -3? It's 7. And now we're halfway there. Now what about this? It's the first one evaluated at the second one. And what is f evaluated at 0? It's 11. And what is g evaluated at 11? It's 0. So again, we get back to what we started with. It's not enough to say it's proven if we're going to take this way. What is this? It's the first one evaluated at the second one. What is f evaluated at 8? It's 5. And what is g evaluated at 5? It's 8. And finally, what is this? It's the first one evaluated at the second one, so g composed with f. F evaluated at -3 is 7, and g evaluated at 7 is -3. So now, after going through all of them, that gets you to x for all x that's in the domain of g. And also we have this for all x that's in the domain of f. So we have checked every single one because this is a relatively small set. So yes, they are inverses. Now you can't do that with this. You cannot check everything that's in the domain because these are infinite domains. The domain here, the domain for this guy is the set of real numbers. The domain for this one is, well, what's 3x minus 4 is going to have to be 0 or positive. So your x values, x are going to have to be greater than or equal to 4/3 for this one. Anyway, let's have a look at this. It's going to be that. Okay. And what is g evaluated at 2? Well, it's going to be 2 squared plus 4 over 3, which is 4 plus 4 over 3. which is 8/3. And what's f evaluated at 8/3? F evaluated at 8/3 is going to be, I'm going to replace x with 8/3. The 3's cancel. And I get the square root of 4, which is 2. And so f composed with g evaluated at 2 is equal to 2. This is not proof that these two are inverses. In fact, they're going to turn out not to be inverses. You'd have to go through every single possible x value, whereas before we had a finite number of choices. We only had to go through 6 different x values. Here, you'd have to go through infinitely many. We can't do that. So what about this? G composed with f at 0. What's f of 0? Oh, so it's going to be g evaluated at that, and g evaluated at the square root of -1, and that does not exist. I think the one they wanted here was, I think that was meant to be a 2. So let's do it for 2. Yeah, because I think they wanted us to compare. Oh, maybe compare these. Let's do it for 2. What is that going to be equal to? Well, what's f of 2? It's going to be the square root of 3 times 2 minus 4, so 6 minus 4, which is 2. So f of 2 is the square root of 2. And then what is g evaluated at the square root of 2? It's going to be the square root of 2, all squared, plus 4 over 3. When I square a square root, they undo each other, so I'm going to get 6 over 3, and that's going to give me 2. So that one works out. What about f composed with g at 5? Well, that's going to be f evaluated at g of 5. And what is g of 5? G of 5 is going to be 5 squared, which is 25, plus 4 over 3, which is 29/3. So if I want to do f evaluated at g of 5, that's f evaluated at 29/3. And if I plug in 29/3 there, the 3's cancel, and I get the square root of 25, which is 5. Okay. What if I do this? That's g composed with f evaluated at 3. What is f evaluated at 3? It's going to be the square root of 3 times 3, so 9 minus 4, which is the square root of 5. And now what happens if I plug in square root of 5 into this formula? Well, I'll get the square root of 5 squared, which is 5, plus 4, which is 9, 9 over 3, which is 3. What about if I do this one? What is g evaluated at -1? Well, g evaluated at -1 is going to be -1 squared plus 4 all over 3, which is -1 all squared is +1, so I get 5 in the numerator. So this is the same as f evaluated at 5/3, and if I plug in 5/3 for x, then I'm going to have the square root of 1, which is 1. Now notice that those two are not the same. They're not the same. So I could conclude from that alone that f and g are not inverses. What happens if I try and do it in that order? What is f evaluated at -1? If I plug in a -1 there, I have the square root of -7, which does not exist. And so that's a contradiction, and so this does not exist. So these are not inverses. As soon as you find one that doesn't work, that doesn't give you what you started with, you can conclude that they're not inverses. But another way is you can look at this graphically. This is not a one-to-one function, so it doesn't have an inverse. If I try and graph this, so I've put the formula into my calculator, and if I look at the graph, that does not pass the horizontal line test. So G inverse does not exist. So it's impossible for those to be inverses. How could I fix this? I could fix it by restricting my x values to be 0 or more for G. So if I have a new function, so the restriction is different, then that function would look like that, and that would be a one-to-one function. It would have an inverse, but I don't have the restriction there, so f and g here are not inverses. Finally, what if you have the formula and you're told to find the inverse? Well, step 1, replace f of x with y. Step 2, swap the x and the y. And step 3 is to solve that thing for y. Okay, the first thing I'm going to need to do is raise both powers to the 1/3. And so these undo each other, and I just have that. Now I want to get y by itself. Multiply both sides by 7. Then add 2 to both sides. So I have that y is equal to 7 times x to the 1/3 power plus 2. And now I have my answer here. I just replace y with f inverse. Or you can write the 1/3 power as the cube root. So 7 times the cube root of x plus 2. That is my inverse. And that finishes this video.